How's it going, everyone? So, before we dive into the episode, I really want to say thank you to everyone that is listening in, that's tuning in, that's enjoying this content and getting value from it. I really love that. That's why I do it. But there's a huge amount of you that are listening that are not subscribed, not following the podcast. And I really want to encourage you to please follow and subscribe to the podcast on whatever platform you are listening or viewing this on. It really helps out the podcast. It helps out the algorithm. It helps more people hear this content that you already find helpful and that they hopefully will as well. So if you go ahead and subscribe or follow the podcast on any platform that you're listening on, and please share it with your friends, that'll be great. All right. Thanks, everyone. Let's get into the episode. How's it going, Eric? It's a real pleasure having you back on the podcast. You know, the first one kind of like cracked my mind open, so to speak, with AI. You know, I think when we were first talking, OpenAI had come out with their version 3, right? And you know, now they're on version 4 with 5 quickly coming out. I think is what it is. It seems like AI is, man, it's like it's in its infancy, you know, in terms of technological evolution. I would say it's like in its infancy, but the impact that it's having is growing significantly and it's rapidly changing. Would you agree with that?
Uh, yes and no.
Okay.
So very happy to be back. I've seen that you've done a couple episodes on AI since I was first on. So, thrilled to see that. I think what I would disagree with is that AI is in its infancy, right? Like AI is a pretty old field of computer science. I mean, we've had artificial intelligence in some form or fashion for 70 years, 60 years, depending on where you want to start counting. But we have seen this pretty explosive growth in large language models and applications of like transformer-based architectures, right? So without getting too in the weeds, this particular type of neural network, this transformer-based architecture, has seen a ton of growth in computer vision, natural language processing, right? All of these things. So I think we've definitely seen a lot of growth and evolution and adoption. I think adoption is the big thing, right? Like we've had AI. I mean, you look at like anomaly detection, right? Like good old fashioned anomaly detection, all the way back to like PID controllers, right? In like electrical engineering, those are, can be used functionally as anomaly detectors. You know, those things we've had forever. It's the fact that it's so on the surface now, right? Rather than living deep in a process where it's like, yeah, I don't know, the anomaly detector told us something was weird, right? This is a thing that interacts in forms that lay people are accustomed to dealing with, right? It's you give it text the way that you would give a person. You give it an image, right? And I think that's kind of the big difference and the big evolution, especially in the last like 3 to 5 years.
Hmm. Well, I feel like when I say it's in its infancy, I'm thinking of, you know, seeing where this is going, right? What's that end state? What's that end phase look like compared to right now?
Mhm.
You know, and right now that end phase or that end state is going to make this look like an infant. It's I feel like it could be that advanced. I guess that's where you know, I was getting that idea, but absolutely, I've actually read a lot, a lot of different opinions on like when it started and how it started and things like that. And you know, sometimes it's hard to even like put that together, right? Because we're so used to this, you know, I guess AI advancement that it's hard for me in some cases to say, oh yeah, it started 70 years ago by this thing that, you know, is trivial today. So it's hard to like tie that dot together, I guess.
Yeah, I think that's true, and this is where like the science and philosophy start to meet. So I think two of the things you said make me feel that way, and of course the first is like when did it start? Right? Does it start with you know does it start all the way back with polynomial regression, right? Where you have an algorithm for performing polynomial regression. Is that lemniscue? I don't remember. Someday you can look it up. It's fine. Right? But you can go back hundreds of years if you really want to. And then on the other hand, right, like modern machine learning, do you start with computer vision? Do you start with AlexNet? Or do you start with, where do you start? I think that's where it starts to get into the philosophy. And the other place where I think it starts to get into philosophy is like, what is the end state? Because there are, I think, these varying schools of thought about, oh, okay, so we have this, exponential growth or this, super linear growth or whatever. Is that sustainable and for how long, right? Is there a period where it's going to level off? Because I mean, I've been doing this long enough to remember, gosh, back in like 2012, when people were saying like, oh yeah, like computer vision is practically solved and we'll have full self-driving cars within 5 years. And here we are in, 2024. And, say what you will about Tesla, we can leave that whole conversation to the side, but even that isn't full System 5 self-driving, right? It's just advanced lane control and speed control.
Isn't that considered to be like I think I read it was like level 3.5 or something like that. I mean, I'm not really even sure what the levels are. If you don't mind, would you be able to go over it real quick, like just a quick gloss over it?
Yeah, so this is not my ultimate area of expertise, but essentially level 1 is like cruise control, right?
Right.
Level 2 operates on 2 axes. So that is the adaptive cruise control, right? Like, even my, Toyota Corolla has that, where it's like, there's a car in front of you, so we're going to slow down, right? There's an obstacle in front of you, so we're going to slow down, even though cruise control is set to 55 or whatever, right? And then the lane management, so that's, forward and back and left and right, right? That 2 axes. Where it says like, okay, I know where the lanes are and I'm going to keep you in the lanes, right? And then level 3 and 4 are blurry to me. But level 5 is like no human intervention whatsoever. General purpose, anywhere, right? Can go anywhere, can do anything. If I remember correctly, level 4 is that it is able to drive under any conditions within a restricted environment. So if you think about like Waymo's robo-taxis in San Francisco, those are, I believe, level 4 systems. But those also use, right, a lot more than computer vision. They're still using LiDAR. They're still using all of these other things. So it's not something that is nearly as advanced as we kind of hoped it would be, right? These self-driving cars that use computer vision systems, they are still struggling with things like, they struggle with object detection, right? Like they aren't even exceptional at object detection. And they're even worse at object detection when like it's raining a little bit or it's foggy or, it's late at night or there are, street lights are out or whatever. All of these things are just limitations of the system, which isn't to downplay how incredible it is that it even exists, right? Like that's cool. That's amazing. But there are limitations to these systems. And I think that if you look at the progress in computer vision, we did see a huge spike after like AlexNet and all that. And then over the last several years, probably since about, vision transformers were the last, I think, like really big advancement. And if you have listeners who are like deep into computer vision, they can, write me nasty emails or LinkedIn messages and tell me how wrong I am. But those systems haven't really continued to grow at that rate. You saw this huge explosion, and then it's an S curve, right? It's a sigmoid function. Which is something that we in artificial intelligence should be really familiar with, right? You have that flat line and then exponential growth and then a flat line, right? So the question really is like, if it is an S curve, right, and not exponential growth forever, which I think is a tough conjecture to justify, right? That's a tough assumption to make. The question really becomes, where on that S curve are we, right? Are we toward the bottom or are we toward the top? And that's something that is hard to know until we really experience the state where it's like, okay, yeah, this thing came out and it was trained on 10 times as much data with 400 times as much compute, and it's only like 20% better. Like, okay, well, now I think we're hitting the point where we're at the top of that curve. Right?
Yeah, it's like that saying, right? Is hindsight is 2020, right? You don't realize you don't realize how easy things were, right? For instance, when you're a kid, when you're a teenager, all you want to do is become an adult, right? You get to drive, you can travel, you can do whatever you want, you make your own schedule, whatever it might be, right? And then
Mm-hmm.
you become an adult and you're like, man, I wish I was a kid again.
Right.
Like like I didn't have a mortgage, I didn't have to worry about paying a car note or anything like
Mm-hmm.
that. Student loans were not a thing. It wasn't even a thought in my mind.
Oh yeah, if
Um,
I trade places with my 7-year-old, I would do it in a heartbeat. It's
yeah,
fine. You can work, you can do all the things, you can go to the grocery store. I'll just like hang out, go to school, have recess, play on my iPad. Yeah, I'm about that. I would absolutely.
yeah, absolutely. Predicting where AI is going is extremely difficult. What I, I guess what I still kind of fail to understand. I mean, this podcast, right, with this question alone, could probably go for days, right? But what I failed to understand is the evolution of the AI chip, right? So that's really interesting to me because it's like I guess one of my questions would be, at what point in time did someone determine, whether it's NVIDIA, Apple, whoever, right? I
Mhm.
don't know who determined it, but at what point did someone determine, okay, we need a dedicated chip, a dedicated hardware module just for AI, and oh, we're going to build this whole, ecosystem like NVIDIA, for instance, as CPUs that are just for AI. I'm not trying to, this podcast isn't sponsored by NVIDIA in any way. You only work at NVIDIA. But again, your thoughts aren't NVIDIA's thoughts or anything like that. We're just speculating on information that's out there.
Yeah. So I mean, okay. So I'll say the original usage of GPUs for deep learning, right? Because again, when we talk about AI, like AI is this whole big thing, but I think it has become shorthand for deep learning, right? Obviously, AI includes things like expert systems, traditional statistical machine learning, like logic programming, which is my personal favorite because it's a form of generative AI that's based on good old fashioned AI, not the modern, the deep learning paradigm. I think it's really cool. I think it's neat. But anyway, I'll put that to the side. I mean, you go back and you see that CUDA, the compute unified device architecture, on NVIDIA GPUs has always been this like massively parallel processing framework, right? You have your CPUs, your general purpose CPUs, you have your RISC CPUs, you have all of these different, you know, CPU architectures and instruction sets and whatever. And what CUDA kind of did was look at computer graphics as this massively parallel computation. And specifically, computer vision has always dealt with matrices, right? It deals with sensors, really, right? The RGB channels, and then you have your image, which is like n by, and so you have an n by c, right? Your length, width, and then the depth of the tensor. Right? Those are how you produce computer graphics. It turns out that in deep learning, you're dealing with the same sort of thing where you have these matrices, right? You're doing these massively parallel matrix multiplications across these different channels. And then bouncing them forward. GPUs were just kind of well suited to the task because ultimately producing computer graphics and doing deep learning is under the hood, the math behind it is a very similar type of math, right? It's massively parallel matrix multiplication. The development of CUDA led to cuDNN, which all kinds of frameworks have been built on top of that, right? You have your Torch and your Keras and your TensorFlow and Theano, if you're an old head, or Chainer, if you've been doing this for 100 years, and more modern frameworks like JAX, right? And they just take advantage of that hardware parallelism. So that's how these sort of chips have become so ubiquitous in AI. And then when it comes to the more AI specific hardware, right, this high performance computing that's not really a consumer grade graphics processing unit that happens to be good at this thing, but are more specifically designed for it. It's just kind of looking at, okay, well, where are those differences between the parallel matrix multiplications you're doing in computer graphics and the ones that you're doing in deep learning? And then how can we enhance the chip to be better at deep learning than it is at computer graphics, right? They'll still render images, right? If you want to plug into your, RTX A6000's display port, you can. I don't know why you would do that, but you certainly could. It's just that it's going to be more performant tasks like deep learning because that's kind of what it's designed for.
That's interesting. So can we touch on what deep learning is, right? Because from an uneducated perspective of AI, right? Like, I'm getting my PhD in securing satellites and preparing them for quantum communications, right? And it's so very close to AI that I actually have to read the white papers on AI and all this other stuff, right? So I'm still under the impression that deep learning is like hook it up to the internet and let it go learn for a couple years, right? What is deep learning?
So at a basic level, right, like the simplest version of deep learning is you think about like put yourself in like, I don't know, 10th grade, right? Go all the way back to grade school and remember your y equals mx plus b. So you've got your y and you've got your x, and you're trying to find the slope and the y-intercept. Now, and then you have to do that with matrices, right? Where instead of finding just the number or the fraction for the slope and the number or the fraction for the y-intercept, you have to do this with a matrix, right? And for anybody who doesn't know what a matrix is, it's like, think about like an Excel spreadsheet, right? You have a certain number of cells, and each one of those cells has the weights in it. What you're trying to do is take your collection of x's and y's and find the best and b so that you have the least amount of error, right? So that if you plug in an arbitrary x, which is going to be a vector since you have matrices, you're going to get a y that's close to it. And then the other thing that it does is on top of that, x plus b, it wraps it in a nonlinearity, right? So nonlinearity is sort of what it implies, right? It's a function that isn't linear. So, some common ones are like the ReLU, which is just the max of the output, and 0. So if it's 0 or less than 0, right? If it's not a positive output, then you get 0. Otherwise, you get the output of the function, right? Your mx plus b. Sigmoid is another one, which is basically an exponential function that maps it between 0 and 1, right? There's a whole bunch of different nonlinearities. If you Google activation function, you'll find thousands of them, right? Like there's a whole literature just on activation functions. But at the end of the day, that is what kind of gives it this spiking. All of this is inspired by human biology, right? So the neuron activation on or off, right, is 1 or 0. And so you get that spiking through these activation functions. So that's a single neuron, right? Is that y equals mx plus b and a nonlinearity on top of it. In a neural network in deep learning, you have many of these neurons that are interconnected, and you have what makes it deep is that you have multiple layers. So the input to the next layer of the network is the output of the previous layer. And you basically stack these on top of each other and then get your output. There's all kinds of fun stuff in there, right? Where like, that describes a good old-fashioned multi-layer perceptron or like, dense neural network. But there are transformer blocks, there's recurrent blocks, there's all kinds of fun stuff you can do inside of those neurons. But essentially, like it all boils down to that mx plus b and then a nonlinearity on top of it.
So in terms of, let's think of in terms of OpenAI and ChatGPT for a minute. basically a large language model that interprets language and provides responses based on the broad knowledge that it has. Are there limitations to like what you're able to teach it in terms of I've already given it all the information that I have available, right? What's the next evolution to teach it more to make it smarter, right? What does
Yeah.
that look like?
If I had the answer to that question, I would. I don't know if I would have time to be on a podcast at all. I wish I had the answer to that question. But that's a real problem that we're running into, right? Is like we've basically exhausted the world's greatest repository of knowledge, right? The people training these large language models, whether it's OpenAI or Anthropic or whoever, like they've collected basically everything that's out there. And, that is a huge limitation, right? Once you've trained it on all the stuff, how do you get it to be better? And there's some applications of synthetic data, right? Where you have these models generate new data that carries its own risks with it. If you start training models on synthetic data, it experiences something called mode collapse. So basically it starts but let me back up. What these models are really doing, right? Whether they're the instruction-tuned GPT-4 that you're using with ChatGPT, or they're more of a base LLM, right? They're essentially doing next token prediction. And think of a token as a word, right? It's not exactly, but close enough analogy. It's trying to predict the next word. So the trouble with synthetic data is that you give it this input, you get this output that's synthetic, and it's generating the next word by picking the most probable, subject to some stochasticity, some randomness, right? It's picking the most probable next output. So if it starts generating, do you want to go to the next word's probably going to be like store? Do you want to go to the mall? Do you want to go, right? Somewhere you might want to go. And as you continue to train this thing on data that it generates, you're raising the probability, because it's seeing these things more often, you're raising the probability of each one of these tokens. And so essentially, you're taking this beautiful heterogeneous probability distribution, this distribution over distributions, and you're slowly collapsing it into a single point, right? Where if you keep outputting the most probable tokens and then training on the most probable tokens, it's just going to continue reinforcing itself until it can't do all that, general stuff, right? There's a new paper on this that came out a couple of years ago. Training on synthetic data causes catastrophic forgetting, is what they call it. And, this is something that, again, we take natural language, which is the hot thing right now. That's what I work in, right? It's like securing large language models. But if you look back at computer vision, again, if you've been doing this a while, you look at generative adversarial networks, GANs. This was a well-known phenomenon in GANs, right? This is something that people who trained GANs were super familiar with, is you had to watch out for mode collapse because you're generating something, you're getting an error, and then you're passing that back in as your next step in your training phase. And if you're not careful, your GAN will just collapse to this single best possible output, and it loses its ability to generalize.
Wow. That is really fascinating it would how it would basically, self reaffirm and push more importance on a certain, topic or language or whatever it might be. And then it just works out all the other stuff from its system. It's like, well, all of that stuff isn't important. I'm going to put all of my processing power towards this thing, right? That seems to be really important right now. It seems like that could be really helpful for some use cases, like thinking of like medicine, for instance, or engineering a new type of structure, whatever it might be, right? Like you could think of a lot of critical services where reinforcement would benefit in some ways, to focus it, on a certain topic or a certain situation. So I never thought of how reinforcement of these things would force it to, collapse in on that one topic. That's really interesting.
Yeah, it is really interesting. And like synthetic data is not all bad. It's just that if you use too much of it, it can become a problem. But it's also like super important to use synthetic data in certain cases where the data is rare, right? Where you don't have a lot of data. Because again, these models are trained on huge, huge amounts of data. It's just like incomprehensible
Mm.
amounts of data. So if you're trying to train something in, say, like the cybersecurity domain, right? You want to train it on logs. Okay, well, you have your logs, but what if you need more logs? Like, do you just wait? Do you wait a year to get more logs? Well, maybe you can feed your logs into a thing that allows you to generate things that look like your logs. And now you can say, okay, these are normal logs. This is what, this is what our system looks like. We're assuming we're uncompromised, which is like a heavy assumption, but put that to the side, right? So this is what the system looks like under normal operation. Now you have enough data to start training your thing to do that anomaly detection, right? Because maybe otherwise you don't. It's easy to come across malicious traffic, right? You can generate basically infinite amounts of malicious stuff. You just pop it in a sandbox and dump the logs, right? But it's a lot harder to generate things that are both benign and look normal, right? So not just benign and nobody's using it, but benign and people are interacting with the system.
Hmm. Do you think, I mean, this is obviously purely, hypothetical. Do you think that cloud providers are doing that somewhere, somehow? Because, I mean, think of the vast amount of the logs, just the logs, not even talking about the data itself or anything else like that, the attacks that,
Mhm.
are launched at them and everything else like that, right? If you're training it on data like that, it wouldn't be very intelligent to not use that data and train an AI with it. Now you have, in security terms, now you have, the greatest SIM that ever existed, right? There's nothing that would compete with that, like, ever. Do you think that that is a route that cloud providers could take?
Two things. One is it a route that cloud providers could take? Maybe. So I'm extremely not a lawyer. I'm as much not a lawyer as you can possibly be.
Of
Uh,
course.
but the agreements between the CSP and their customers would kind of predicate the level of access to logs that they have, right? They might have access to infrastructure logs, but they may not have
Hmm.
authorization to access, your NetFlow logs or your, uh, whatever, your WAF logs, right? They may not be able to see that legitimately. I'm sure that if somebody were determined to, they probably have capabilities, but like that would be kind of, I think that is the sort of initiative that would be hamstrung more by lawyers than by technical capability, right? Because the CSPs, you think about Microsoft, Google, Amazon, the three big ones, they're also companies that are training and putting out huge language models and doing really incredible research in artificial intelligence, right? Microsoft and Google in particular, right, have been doing phenomenal AI research and security research for quite some time. And like a bunch of people want to occasionally cuckoo on Microsoft's security posture, right? Like they have gotten a lot better about being forthcoming with security information and publishing security research. Shout out to my Microsoft friends. Now, would that lead to a SIM to end all SIMs, right? The one SIM to rule them all. I think it depends on how optimistic you are about AI alone, right? Because you could use that for incredible, SIM rule development, and you could definitely have a world-class SIM based off of that data. But a lot of like the really good SIM rules, handwritten rules that are written by, security experts, right? They're things that are known to be bad. Because one of the things with security data is that there's a lot of noise there's a lot of weirdness, and there's a lot of things that to an ignorant party might seem really important that don't end up actually mattering and should not be used as a factor. I'll give you a concrete example where once upon a time I was working with a team and we were trying to train a malware classifier. Right? So we had this giant corpus of malware, huge corpus of malware. And we took all of these features, we featureized the thing, and we, trained this machine learning system. It was a tree-based architecture, right? A decision tree-based architecture. Because this was, a few years ago. Right? And it had this great performance. It did a great job detecting malicious samples. Like false positive rate wasn't too bad. And then we looked at the components that were considered most important determining whether or not something was malicious, right? The most highly weighted components, kind of the top of the tree. And item number one was the compiler. It was a compiler. If it was compiled with Borland Delphi, it's malicious. I don't know if that's true. I don't know if that's great. Item number two, the second most important feature, so if both of these things were true, it was malware all the time, was if it was compiled in Russian or Chinese. So the language of the executable, right? And what I did as a malware analyst, those two things are functionally meaningless in determining whether or not something's malicious. And it was just an artifact of where our samples came from, right? So, when you're optimizing for those things and you're doing it in a way that doesn't account for expert knowledge, where you don't have people who are reverse engineers who are malware analysts looking at this, you might think, if you're, a layperson, like, well, look, the accuracy is good, the F1 score is good, like, we're happy with this thing. And then you look at the features that matter to it, and it's like, does it import WSOC2, right? Does it do networking? Is like the seventh most important feature on that list. And it's like, I don't know, man. To me, that is like one of the more important features for me to look at, right? Does it modify registry keys, right? Like these sorts of things are going to matter. Whether it's Chinese or Russian doesn't matter. These are the sorts of things that would make it hard to just take a bunch of data, train the world's best sim, and call it a day, right? You still need that security expertise to write the good rules to correlate things.
That is, man, that's really fascinating. I feel like we could literally talk on that for hours. In security, like you said, the attributes, what the malware is actually doing, what the code is actually doing, is far more important than its origin.
Yes.
Right? Once you figure out what it's doing, and you kind of attribute, okay, this is typically from China. This is typically from Russia. This is typically from America, right? That's a possibility as well. And I wonder what kind of result, and I mean, this is again purely hypothetical, right? I wonder what kind of result you would have if you trained a model on only written malware, right? And then you had a separate one that was trained on other nation states that are playing in the space, right? And then you use that to somehow inform some other higher tier model that when it looks at a piece of malware, it dissects what it's doing, it tells you where it's from, all that sort of stuff, rather than, because right now it's a manual process, right? You throw it into a reverse engineering tool like IDA Pro, right? And you start going through it, and God forbid they compile, different modules of the code with different languages and things like that, right? Because it just extends your reverse engineering process significantly. But I wonder if that is, a very viable thing. And then you could even use that model to write more malware, right? You could use that model from the malicious side to use it to create like Stuxnet version 5, right? That is undetectable.
Well, that's the thing with a lot of the machine learning systems, right? A lot of these AI systems is that as a side effect of training a model that's good at defense, you kind of get a model that's good at offense, right? You can invert the that's something that we're seeing, you look at large language models, and like one of the big things that people are talking about and concerned about is phishing. And I think that's valid. So the thing about phishing is I don't freak out about how LLMs enable phishing because I have seen people fall for some of the most obvious phishing emails ever written, right? I've seen people respond to the like literal I am from IT, we're resetting passwords, can you please email me the password? But I have seen that in my real life. Things like, do LLMs enhance the ability to scale, right? Does it let attackers be lazier? For sure. But when you train a large language model that's designed to help anybody write an email, if I go to ChatGPT after this or Perplexity or whatever, and say like, write an email to Joe Self thanking for having me as a guest on his podcast. That same system also has the ability to write a phishing email because a well-written email is going to be a well-written email regardless. It's just a matter of whether, you include a link. Right. And so, I mean, that's why like a lot of the user education around phishing, I think is kind of dated, right? Is like look for misspellings, look for, these things. Right? And I mean, there are phishing templates, right? You can go on whatever the current version of exploit.in is, breach forum or whatever, right? Who cares? Go on one of those forums and there are phishing templates. Those are well written, legible. You can have them in any language you want. Great, good. So, I mean, does a large language model really increase the threat landscape? Not necessarily, but does that mean that it's a dual use technology that we need to be aware of? Yes. Right? And so when you have coding assistants that can help you write any code, can those be used to write malicious code? Probably. And I think this gets into the big conversation around like model alignment. How do we put safety into models? How do we put safeguards into models? And I think that that's like a good first layer. But I don't think that alignment in and of itself is a solvable problem. I don't think it's a tractable problem, right? To encode these things into the model weights, like at the end of the day, these are just tiles of linear algebra. They don't know anything. They don't think. They don't have values, right? We can't necessarily encode that. But having systems around it that validate the input with respect to some policy and the output of the model with respect to some policy, I think that's where we can start making meaningful gains, right? Because with these large language models, one of the big things that a lot of people don't realize about them is a key difference between these AI systems and like good old-fashioned computing systems is in good old-fashioned computing systems, we have a data plane and a control plane, right? And they're separated. And so you can do things like see something happening on the data plane and say, okay, don't talk to this IP address anymore, right? You're not allowed to go there. And you can manage that at the control plane layer to affect what happens on the data plane. In LLMs, the data plane and the control plane are the same thing. There's only one place to put input. So your system instruction, right, your thing that says like, you are an unbiased, friendly, helpful language model who does X. Great. That goes into the exact same input space as your arbitrary user input. And there's very few mechanisms and certainly no provably, mathematically provably, right? No provably secure way to differentiate them and to have the model treat them differently. It just treats it all as one big input. And those are the sorts of things that make the problem of securing these systems really hard. Yeah.
So, do you think that this is going to turn into a situation with cloud, like what cloud security is currently evolving into, right? Where you have cloud security at such a scale now, right, across so many different domains that it can't be handled by one person, right? It can't be handled by, one person per cloud even, right? you really need to start having like a cloud IAM team. You really need to have like a cloud data security team, people that specialize in it. Do you think that that is also the route that AI will be going? And if so, what do you think those specialties would be?
So I don't think it will go the route that cloud is going. And how it gets managed, I think, depends on how the community, right, like the broad security community, and even more broadly, like the risk community, right? So if we look bigger than InfoSec risks, a lot of AI risks, right? A lot of the trouble that you're going to get into with AI today is falling on the plates of your PCERT and your IR teams, and like those poor people who have to deal with the fact that your chatbot said something kind of nasty, right? Or said something that wasn't actually part of your corporate policy, right? You have the Air Canada instance where it said, something about like a refund policy. They offered somebody a refund or whatever, and that wasn't their policy. And a court made them uphold what their model said, right? Like, is that something that your PCERT should be dealing with? Probably not. Probably not, right? There are certainly potential security issues, but what I've found in AI security, in the security of AI systems, right, rather than applications of AI to general security problems, is a lot of it just comes back to like AppSec, right? We have a retrieval augmented generation system, a RAG, right? It's a language model that talks to a database. And maybe we did a bad job cleaning what should be in the database, or we let the language model read anything in that database, and it should have user base, right? User, you should have role-based access controls. But like, that's annoying to do. You have to make the user authenticate to the bot, and then you have to make it, take a token and pass that token into the database. That's annoying. So we're not going to do that. Like, okay, well, that's your problem. Is like it's bad AppSec practices, right? A lot of it comes back to that. And I think, if AI security ends up being AI risk management, and is that big broad umbrella where like bias becomes part of it, or hallucination or whatever general risk, then yeah, there's no way one person could possibly do that. If you're publishing, if you're a model provider, if you're hosting a model that end users interact with in ways you can't predict. But if we slow it down to security, I think it's maybe not quite as complex, because a lot of this is just architecture. And it's like you have this thing that takes English language input and generates SQL queries. It's like, okay, well, maybe you should do some output validation. Don't
Right.
send arbitrary SQL to your database. We know this. A lot of these things are familiar to us, but when they get abstracted away through this large language model, we kind of have trouble seeing the trees for the forest, as it were. We get stuck on just seeing, okay, this is some big thing that has an English language interface and talks to our database. Who's talking to it? Do we pass their user role through, or does it have the ability to read the whole database? And you can't really trust the language model's output. I think it goes back to that sort of stuff, right? Taint tracking, right? Stuff that we've noted about, which is like, if you talk to an AI system and it has the capability to go retrieve data from the internet and then process that data from the internet, then it shouldn't be allowed to take its output from the internet and interact with privileged systems, right? You wouldn't let a random internet server do things on your systems, right? These are the sort of things that we need to be cognizant of. So I don't know that it's necessarily going to get to that point, but we have our baby steps, which is like good AppSec practices, and then we can start getting into the broader, how do we do AI risk management for organizations? And I think that's a much bigger and harder problem that can't be solved by a single person.
So it's It's really fascinating, this entire new area, right? That just kind of spurred up into everyone's forefront of their mind, right? Now, do you know roughly how large the LLM is, like how large the biggest LLM is right now in terms
Uh,
of like data size?
well,
I mean, I don't
no.
even know how to.
So most people believe that the largest LLMs on the planet are either GPT-4 or Claude 3 Opus. Like those seem to be
Mhm.
the largest, most capable models. Claude 3 Opus is, by the way, really cool. I am not paid by Anthropic. I just think it's cool. It's the first model in a while that's really surprised me with its capabilities. But they have not, neither Anthropic nor OpenAI, has said how many parameters it has, how many tokens it's been trained on, right? All of that is information that they haven't released to the public. So we have some pretty large open weight models, right? Some people say open source, but if the data is not public, I'll get off my soapbox. Right, these open weight models, and so we do have some pretty large ones out there, right? I mean, Grok is quite a big one. Mixtral is a pretty big mixture of experts model. That one's good. You have a couple of like 340 billion parameter models out there. I think there are even some meaningfully larger ones that have been other weights released, right? Yeah.
Well, so that's I ask because the parameters is a hard thing, I think, for people to understand the size of the data. Do you know what that roughly would translate into in like petabytes or even exabytes at this point?
So I think the parameters of the model and the training data are kind of distinct things, right? So the parameters of the model basically just say how much RAM it's going to use, right? How much VRAM or how much whatever, right? If you want to run it on CPU because you're an insane person, that's fine. Have at it if you
The
want to run
electric
a
CPU.
340 billion parameter model on your CPU with, a terabyte of RAM, I guess, right? But these models, the parameter count basically says how much compute it's been used, right? How much RAM and GPU, if you RAM, GPU, CPU, whatever, right? The training data, on the other hand, there's a paper from a couple of years ago, the Chinchilla paper on Google, that actually suggests that there's like an optimal number of tokens to train a model on based on the number of parameters, right? Like most of these are following that chinchilla model, because you don't want a model that's overtrained or undertrained, right? I mean, hypothetically, you can train a 500 billion parameter model on no data. It's not going to be any good, but you could do it, right? Now, looking at that, I mean, we're talking, gosh, I mean, if you have like 8 trillion tokens, you're talking like several petabytes of data.
It's an insane amount of data, right? Where do you even start with securing it? I feel like it's obvious what the best practices are for normal security, even cloud security, right? Are those best practices translating into LLMs, or is there something else, that you're starting to potentially even adjust the best practices for?
Yeah. So I would say that like your security best practices, all of your security best practices still hold, right? Like you still want your defense in depth, you still want your role-based access controls, you still want to make sure you're doing input validation, all of this stuff, right? No question about that. Now, I think if we separate the OpenAIs and Anthropics and Googles and Metas of the world, right, and like let them worry about how they protect their training data and model weights from being manipulated. Set that to the side for the moment and think about somebody whose organization is trying to deploy an LLM powered application, right? They want to have some customer facing chatbot, or they want to integrate some natural language interface into their product, whatever. I will say you inadvertently set me up to plug the two open source projects I work on. Right, one of those is Garak. So Garak is like Metasploit for LLMs, right? So it's got a collection of a bunch of different known ways to get language models to say bad things. And you can kind of pick and choose what you're concerned about, right? So if you're concerned that your chatbot is going to give toxic output, right? You're concerned about that sort of thing. Then you can send these prompts. It's like a command line interface, right? And it'll do all the work for you to take these prompts, bang them against your model, and give you a report. So then you can get kind of a sense of like, okay, well, where are the risks associated with this, right? Or if you're concerned about, package hallucinations, which is a thing that is of a non-zero amount of concern to people, right? Like with all the NPM and PyPy package hijacking that you see, right? If this thing makes up a package name and you, okay, sure, import this thing, and somebody has seen that hallucination and put that package into PyPy and it's a malicious package, well, that's rough. That's bad. That's bad day for you. So, you can test for that sort of stuff. There are a couple of different ways to deal with that. If you're training or fine-tuning your own language model, you can try and fine-tune that out, or prompt tune it out, or modify your system prompt or whatever, right? Like that might work. There's also these LLM firewalls, right? I think Cloudflare went out. There's a bunch of companies that have them, right? And those will kind of look for and detect known quote-unquote jailbreaks, right? So like known attacks against these models, the sort of stuff that we have in Garak, right? That's fine, and that stuff is good. Some of it's quite good. One of the other things is the other open source project that I work on, which is called Nemo Guardrails. And so what Guardrails is more of like a dialogue management framework. So you can write these really specific configs, or these, essentially write through YAML files. But this Golang is the language, this abstraction that we deal with. It's like a domain-specific language that lets you say, okay, well, you should only talk about, scheduling vehicle maintenance. And if you're asked about anything other than vehicle maintenance, don't do it, right? Mm-hmm. And it provides this external check on the model, so that when somebody asks a question that's not about vehicle maintenance, you're not depending on the model, which has no separation between the control plane and the data plane, to parse that. It's kind of saying, okay, well, this isn't about that, so we're going to tell the model to do something else, right? We're going to get in between you and the model. And you can make those as complicated as you want. There's a bunch of other stuff in there, right? Like it's a really powerful framework. But these are the sorts of things that you can also put around your models, whether they are something you're deploying yourself, right? Whether you've downloaded Llama 3 and you're using that as your basis and you're self-hosting it in some cloud service provider, or if you're using like an OpenAI or a Cohere or an Anthropic on the back end. Yeah, there are a couple of different ways to both test these things, right? Garak, Pyrit, Pyrit, which is put out by Microsoft, is another framework like this. And then on, the other side, you have your LLM firewalls, you have your Nemo guardrails, you have, there are alternatives to guardrails. I think they're all called guardrails in some form or fashion. Amazon has their own guardrails, but, Nemo guardrails is the one that I know best because it's the one that I work on. So there are definitely ways to start thinking about the AI specific stuff. It just gets back to like, what do you care about? What is the threat model? You have to think about that, right? So if you don't care that your customer service chat sometimes like says awful things to people. You don't care that it's toxic, right? Like it's funny. It's like the Dick's Last Resort chatbot. Great, cool, fine. But maybe you do. And maybe your legal team doesn't want to expose themselves to the liability that comes with having that happen. And in that case, you have ways to test it, and ways to try and mitigate it. And of course, with anything in security, right? Like a sufficiently determined attacker will always find a bypass. These things aren't foolproof, but they can certainly make it a lot better.
Hmm. Yeah, you can make it, reasonably difficult to where it's like, okay, if and or when they still get in, it's like I couldn't have done any more. What do you expect, right? Well, Eric, honestly, same thing as the first time around, right? I feel like this conversation can go another 2-3 hours, right? So I guess that just means I gotta have you back on a couple more times.
Absolutely. I appreciate
Yeah,
it. It's always a pleasure, as always.
yeah, it's such a fascinating topic, and of course, it's at the forefront of everyone's minds now. I think my wife uses chat ChatGPT to write more emails than she actually writes at this point. But Eric, before I let you go, how about you tell my audience, where they can find you if they wanted to reach out to you, and maybe even what those open source projects are that you're working on.
Yeah, sure. So I am on almost no social media. You can feel free to find me on LinkedIn. I'm the only Erick Galinkin. If assuming my name is in the show notes, you can just copy and paste that, and it's probably me wherever you find me. Yeah, feel free to drop me a message there. You can email me, whatever. I'm an easy person to find. It's a perk of being one of one. And then those two open source projects are both on GitHub. Please feel free to check them out and feel free to join the Garrick Discord. That is actually a place where you can find me and pester me directly. And that's, github.com/nvidia/Nemo, Nemo dash guardrails, all one word. And then github.com/ it's currently under Leon DZ, hasn't been moved to an NVIDIA repo yet, /Garak, Garak. Yeah, by all means, feel free to reach out. Love to chat.
Awesome. Well, thanks, Eric, and I hope everyone listening enjoyed this episode. Bye, everyone.